in the row reduced echelon form, right?
Okay, but what about rank then?
Rank is rank is the dimension of row space. So
Rank
rank
is
of row rank is same as dimension of the row space, which is same as number of rows, non-zero rows in the row reduced echelon form. All three things are same.
okay, and we can also find bases using RREF, right?
Yes.
So, what method is more ideal, the row method or the column method?
Uh, it depends on what type of basis you want. If you want basis from the spanning set, then you need to use column method. And if you just want some basis need not to be which may not to be from the spanning set, then you can use row method. Is
Okay,
that
is
what
there
you
any other
are asking?
method?
Yeah.
Okay, okay. Thank you, sir.
Yeah, these are the two methods you can find. Like these are the two ways that has been taught to you. So let's stick to that.
Okay. And is the session being recorded?
Yeah, everything is being recorded, and everything being
Sir,
uh, streamed online. Yeah.
sir, I have a doubt in the cardinality of a matrix.
Okay. So what we will do, I think it's already 4 minutes. So what we will take all the doubts in the later at the end of this today's session. So just keep your doubts with you. So I will be coming back to them. Is that fine?
Yes, sir.
Okay, good. All right. So is everyone able to see the shared screen? And am I audible to everyone?
Yeah.
Yes, sir. But sir, can you
Okay,
change
good.
the layout?
Okay, you want landscape? I
Yes,
will
sir.
do that. Okay, is this
Yes, it's fine.
good? Okay. Uh, so let me start with introducing myself. So I will be, uh, I will also be teaching you along with Sanidhi uh, in alternate weeks or whatever the arrangement is. Myself, Prerak. Uh, so last week, Sanidhi took live session. Uh, so I'm Prerak Deep, and this week I will be taking the live session. Uh, yeah, and whatever doubts you guys may have, we can discuss it at the end of this today's session. There are there is an announcement that quiz one uh, flavors of quiz one is from week 1 to week 5. Okay, so this week's flavors is included in quiz one, right?
Yes, sir.
Uh, and there is one more thing. Uh, so last week, someone was asking question from graded assignment of week 3, which Sanidhi, due to a lack of time, couldn't answer then. So is that person is still here and want to ask the same question?
Yes, sir, I'm there.
Okay, so we can discuss. Do you still have doubt in that question, or is it clear for you?
Yes, sir, I'm not able to understand the question.
Okay, so what we will do, we will also take that question at the end of today's session, if time permits. Okay.
Okay, sir.
Um, yeah, right. So let me start with. So this is the announcement. Yeah, let me start with recalling what we did last week. So last week we studied about dimension of of the span of a given spanning given set of vectors. All right. We also figured out the basis of the span. Uh, yeah, as one of the students mentioned that there were two methods, row method, and the other one was the column method. Okay. So uh, row method is to find out the basis vectors, and column method is to find out basis vector that are coming from the spanning set. All right. So that's the difference between these two methods. Uh, yeah. And there was also rank, rank of a matrix. Rank of a matrix was also discussed last time, right? So what was the rank of the matrix? Can anyone recall?
Yes, sir. The col where it
Sir, the
column rank.
non-zero rows.
Yeah, for the rows we can say the non-zero rows, and for the column we say the number of pivots.
Okay, good. Um, so row rank was number of non-zero rows of what?
Of the matrix
Uh,
vector space.
row reduced echelon
Yeah.
form.
REF.
Yeah, right. And column rank is number of pivot variable, number of pivots in RREF. All right. So let me recall these things with examples as well, so that will be more clear to. So consider this uh, spanning set spanned by vector v1 given by 1 comma 2, vector v2 given by 3 comma 7. Okay. So what do we do first? What's the first step of finding the dimension or basis of this spanning set of v1 and v2? How do we form the matrix from this?
Arrange vectors in column wise.
Okay. Or we can arrange them in row wise also, right? So let's arrange them in. So I've arranged them in column wise, and then what do we do? We perform row operations,
Yes.
right? We want to find out the row reduced echelon form of it. So what is the first operation that you want to perform?
Sir, R2 minus 2R1.
R2 minus 2R1, right? So it is going to be 1, 0, and then it's going to be 3, and then 1.
1.
And, and then what other operation we can operate on it?
Sir, we can
R1,
tell the answer by now only, no?
Yeah, we can tell them, but yeah, we can tell now also. But let me write in the complete reduce form, row reduce form. Okay. So what are the pivot variables? These are the pivot variables, right? So both of them are pivot variables. There are only two variables and both of them are pivot. So yeah, so both of them are pivot. Uh, Now, so what is the dimension of this spanning set?
2.
Two.
Right. Dimension is 2. Okay. And what are the bases of this spanning set?
Sir, 1001.
1237.
Yeah, both of them are correct because we are using column method. So these pivot element tells us that wherever in whichever column the pivot is there, that particular column uh, is going to be the basis of the spanning set. So since it is in the first column, pivot is in the first column. So what is the first column in the beginning? 1, 2, this vector. And now pivot variable is also in the second column. So what is the vector at the second column? 3, comma 7. So 3, comma 7 and 1, comma 2 are basis of this spanning set as well. And further 1, comma 0 and 0, comma 1 are also the spanning set, or also the basis of the spanning set. Okay. So dimension is dimension of the spanning set is 2. Okay. So similarly, there is another example 1, 3, 2. V2 is given by
So what about
3,
rank of
9.
the series matrix? Rank is also 2,
Yeah,
right?
yeah. Rank is also 2 because what is the rank? Number of non-zero
Okay.
uh, rows. So it is also 2. Yeah, good. So this is also equal to the rank of row rank of this. Uh, and now V3 is given by 1, comma 1, comma 2. Now again in this we can treat the vector by row space. We can form a matrix by taking each vector as row. So let's say we denote the spanning set of V1, V2, V3. Okay, this is how I denote the spanning of V1, V2, V3. So 1, 3, 2, 3, 9, 6, 1, 1, 2. So I'm writing each of the vector as row of this matrix. Okay. Now, how do I apply? I just need to again apply the Gaussian elimination. So what is the first operation that we want to do? We can divide R2 by 3. We get 1, 3, 2, 1, 3, 2, 1, 1, 2, right? Then we, and what do we perform? What is a visible operation that you can see?
R2 minus R3 or R2 minus R1 you can do.
R2 minus R, right?
R1.
So what we will get? We will get
0 and C
first row remain as it is, second row becomes 0, and the third row remain as it is.
and
Now
then we
what
can
operation
do
one can?
R3 minus
Ah,
R1.
right. R3 minus R1. Second row remain as it is. Third row becomes 0, and then minus 2, and then 0 again, right? And then what we can do? We can divide R3 by
By minus 2.
minus 2, right? So at the end, we get sorry, 1 0. Okay. Now, how many pivot variable are there? How many pivots are there?
2.
Two pivots are there,
Two.
right? And so pivot number of pivots is 2. Number of non-zero rows is also 2, right? Now, what is the number of pivots? What does number of pivots say? It is equal to, it is column rank, right? And what is number of non-zero rows? It is
Row rank.
row rank, right? So in this example as well, we can see that column rank is equal to row rank. In the previous example as well, we saw that number of pivot, which was dimension of the spanning set, is 2, and row rank was also 2. Okay. So in general, column rank is always equal to the row rank for a matrix. Okay, as well as one can write down the dimension of V. Now, what was V? V is the spanning set of V1, V2, V3. So dimension of V is again number of pivots, which is 2. Uh, yeah. And what are the bases? Now, basis in this case, uh, this vector, the first row, and then the third row.
Third.
So basis uh, set of bases is precisely 1, 3, 2 and 0, 1, 0. Okay. So in this case, the basis that we obtained is not from the spanning set uh, because we use the row method. But if we had used the column method, we could have obtained basis from the spanning set as well, like in the previous example. Is it clear to everyone?
Yes, sir.
Yes.
Good. So today's topic is nullity. Okay. So, for example, in this matrix, so the matrix that you form out of these three vectors, how did you form this matrix? We form this matrix by taking rows, uh, by taking vectors as rows of this matrix. Okay. And then we define this matrix. Now, in this matrix, you can see that there are uh, so one can see because there are, you can think of that there are three entries in a row, but there are only two pivots. So there is a gap of one number. Okay, three three entries in a row, but only two pivots. Okay, so there is one missing. So what is that one? Where is that one vector is missing? So what is happening to that? So that hints you something which is called nullity. But let me say it more precisely. So today's topic is null space of a matrix A or a linear system of equation. Okay.
Normally in basis, we will rearrange the rows with the zeros in RREF, right? So since we need to select the basis, that's why you haven't done it. Or...
Yeah, one can do that also because yeah, all the zero rows should be at the end. So one can do that also in order to obtain that. But yeah, in order to obtain the proper row reduced echelon form, one need to replace R2 by R3. That is a correct point. So let me not confuse you with
So that is the
this.
reason we are using column method to when we
Right,
to select from the original spanning set as the vectors, right?
right. Yes. Column method is to select vectors from the original set, basis vector from the original set.
Okay.
Right. So So we have seen that a given given linear system of equation can be realized as a matrix. For example, uh, if I have 3x1 plus 4x2 is equal to 5, 7x1 plus 8x2 equal to 6, and x1 plus x2 equal to 1, then I can realize this linear system of equation. Each of the equation is a linear equation, and I can realize this linear system of equation as a matrix 3, 4, 7, 8, 1, comma 1. Okay, a 3 cross 2 matrix that is getting multiplied with x1, x2, which is a 2 cross 1 matrix, and giving another column matrix, which is 5, 6, 1, which is 3 cross 1. Okay, so this system of equation can be realized as a matrix multiplication. Okay, and then you have seen that how to solve this system of equation by how do we solve this system of equation?
Gaussian
Yeah, by
elimination.
Gaussian elimination.
method.
But first you need to first we need to do something. Yes, augmented method. Right. So from this, to solve that, we first uh, obtain a augmented matrix which separates the solution set by a vertical line, and this is how you obtain this matrix, and then you perform Gaussian elimination over it, right? To obtain something which is called row reduced echelon form of the matrix on the left, and then the solution space on the right, right? And then you get the solution, whether it is the solution exists, there are infinite solution, consistency, inconsistency, and all these things. Now, uh, so these systems are called heterogeneous system because on the solution set are non-zero value. Okay, so if the solution set, in particular the column vector on the uh, right hand side is 0, then we call that to be a homogeneous system of linear equation. So in particular, if I have a system like this, so this is called homogeneous system of linear equation, and the solution set of this, okay, the solution set of uh, above system is the null space, okay, or is called our solution set of the system is called the null space of the corresponding matrix. Okay, so what is the corresponding matrix here? The corresponding matrix is going to be 3, 4, 5, 5. Okay, so this is the corresponding matrix A, right? And the solution set of this system of an equation is called the null space of this uh, matrix, corresponding matrix A. All right. So let us first find out what is the solution of this particular matrix. Okay, so let us take this example and find out the null space of this space. So 3, 4, 5, 5, and since we want to find out the solution, again we consider the augmented matrix with 0, 0 on the solution set. Now we perform the Gaussian elimination. So what operation first we need to perform?
Row 1 by 3.
We can, sorry?
Row 1 by 3.
R1 by 3.
R1 by 3. Okay, and R2 by 5. Let us do both operation at the same time. because they are independent to each other. So 1, 4 by 3, 0, 1, 1, 0. All right. Uh, Now, what can we do? We can
R2 minus R1.
subtract,
Right.
yes, R2 minus R. Correct. So 1, 4 by 3, 0, 0, 1 minus 4 by 3, which is going
Minus
to be
1 by
1
3.
minus 1 by 3. Sorry. Minus 1 by 3, 0. Right? And now we can multiply it by 3.
To R2.
Sir, minus 3.
Yes, minus 3. Right. 4 by 3, 0, 0, 1, 0. Right? So now what do we see from this? What are the solutions?
No solution, right?
There is a solution, right?
Yes, sir.
X1 equal,
X1
there is
is
a,
equals to. Yes, sir.
Yeah, x2 equal to 0 and x1
yeah,
equal to 0.
x2 equal to
X1 is
0,
equals to minus 4 by 3 x2.
x1 is equal, x1 plus 4 by 3 x2 is equal to 0, right? This is
Yeah,
what
x
we
Yes, sir.
get
equal
from
to
this
0 as
equation.
well.
And now if you place x2 equal to 0 in the second equation, what do we get? We get x1 also equal to 0. So x1 equal to 0, x2 equal to 0 is the solution uh, of this. So basically it has a unique solution, right? It has a unique solution. So what do we note from this? So unique solution, which is uh, unique solution 0, 0. And the second thing that we note in this example is that we have, because the solution set was 0, 0, we didn't perform, there is no change happened in the solution set, solution vector, okay, which is 0, 0 vector. So we don't need to keep that uh, vector while solving this. We can remove that vector. We can just simply work with the corresponding matrix and perform the Gaussian elimination. Okay, so the solution vector 0, 0. Okay, so basically the vector that I'm referring is this 0, 0 and A. So this vector is redundant. Okay, there is no use of this vector while in the calculations. Okay, in the calculation to row reduce vector, because it remains 0, 0 while computation. So we can remove that. Okay, we don't need to carry that along during the calculations. Is that clear? Right. Now let's come back
What
to
about
uh,
consistencies?
sorry.
What about consistency? How do we find it?
No, it is always 0, right?
Okay. Huh, okay.
In RREF, the pivot is the only non-zero element in the column. Yeah, so one can do one more step and then make it 0, but uh, I haven't done that. I just stopped at this point. One can do one more step and then obtain the row reduce while taking this to be 0. Okay, so there is no problem with that because it doesn't affect my solution, so I stopped at that point. Right. So what I was saying, nullity. So what is the solution set of the above system? This is the null space. This is how it is defined. Solution set of the above system. So what is the solution set that we got? So solution set was 0, 0.
0,
So
0.
what is the null space of this? Null
0,
space
0.
of A is just 0,
0,
0.
0.
Okay. Now what is the dimension? Dimension of this null space?
It's 2, right?
0, right?
0, sir.
It is 0.
Right.
Okay. So why it is 0? Because uh, there is no independent variable. Both of these variables are dependent variables. There is no independent variable, so it is zero. So let me take one more example to discuss that. So in this case, both of them, zero, x1 and x2 are uh, dependent variable because you are able to find out the values, their exact values. So they are dependent. Okay, but so and there is no independent variable. And number and dimension of a null space.
Dimension is non-zero, Rose, no?
No, no, that is the dimension of row space. That is a rank. I'm defining something new here.
Okay.
Okay, it is a null space that we're talking. It is not the uh, row space. Okay, okay. So let's forget this for now. Let me. So till this point, it is fine, right? Null space of A, which was nothing but the solution set of this system of equation. So it is the null space. So now let me write it more uh, formally. Null space of a matrix A is nothing but set of all vectors in Rn such that Ax is equal to 0, where x is a vector, Ax is equal to 0 vector. Okay. In particular, if A is going to be some matrix of like above, A11, A12, A22, A23, A121 or A22 type. Okay. And there is x1, x2, and then there is 0, 0. So this can be thought of as a homogeneous system of linear equation and solution set of a homogeneous system of linear equation. Okay, let's do one more example. X plus
So every time the null space will be zero.
no. I'm giving one more example, so you will get to see. Okay, x1 plus 2x2 and 3x1 plus 6x2 is equal to 0. So this is the given linear system of equation. This is example number 2.
This won't have any solutions.
This won't have any solution.
It will have
Let's check
solution,
that.
sir.
Okay, so
Okay.
it's x1. Both are x1 plus
X1 is
x2 equal to 0.
dependent and X2 is independent. Sir.
Right. So let me first write down the corresponding matrix A. So what is the corresponding matrix A?
1, 2, 3, 6.
Right. Now, what is the augmented matrix in this case? Augmented matrix in this case is going to be 1, 2, 3, 6.
6, 0, 0.
Right. And then let's apply the Gaussian elimination method. So what is the what
R2
operation should I
minus
apply?
3R1.
3R1, right. So what do we get? We get 0, 0. All right.
Yes.
And now there is only one pivot, right? How many number of non-zero rows?
1.
1. Number of pivot is also 1. So the other vector, the other variable, this other variable is called the
Independent variable.
independent
Variable.
variable, and the
Dependent
pivot
variable.
variable is the dependent variable. Why? Because if you write down this, the solution set of this, you will get x1 plus 2x2 is equal to 0, and there is no condition on x2. Okay, x2 is free. X2 has no condition. All right. So
So
Yes,
it
sir.
has infinitely many solutions, no?
exactly. So that is free. It can take any value. Okay. Independent means it is not depending on any value. It can take any value. That is what independence means. That is what independence is. That is what freedom is. Right? So it can do whatever it want. It can take whatever values it can take. Right? So x2 is varying x2 varies in R. X2 can take any value, but x1 depends on x2. So x1 becomes the dependent variable, and x2 is the independent variable. Okay.
Sir, like we can even consider x1 as independent and x2 as dependent, right?
Yeah, one can do that as well, but let's not confuse uh, at this moment. Okay. So let me write down the solution set. So what is the solution set? Solution set of this linear system of equation.
It's
Solution set is set of all vector x1 comma x2 in R2 such that ax was 0. Okay. Now we have seen that after performing the Gaussian elimination, we saw that this ax equal to 0, this becomes to the expression x1 plus x2 equal to 0. Right? Sorry. So this becomes this expression. Now what you can do? Now you can replace x1 in terms of x2 or x2 in terms of x1. Okay, as one of you was mentioning. But let's do this thing that you switch x1 in terms of x2. So now x2 becomes minus 2x2. Sorry, x1 become minus 2x2, x2. All right, in R2. Okay. Now, in order to find out the basis of this null space, okay. So till this point, the solution set is clear to all of you. All right. How do we get the
Yeah.
solution set? It is not 0, 0. Okay. And what is the dimension of this solution set? How to find out that? For that, we uh, for each now in this case you can clearly see that you can take x2 out, and this is just 2 comma 1, right? Uh, where x2 belongs to R, right? So you can take you can think of x2 as some t variable in R. Let this, so it becomes t times 2 minus 1, where t is in R. So it is nothing but the spanning set of 2 comma 1.
Sir, excuse me.
Right. Yeah, please go ahead.
Sir, in the third step which you have mentioned, I'm not clear.
This
This,
one?
yes, sir.
Okay. So what does this expression do? This expression tells that x1 is equal to x2. Let me just write down one more step. Okay.
Sir, it tells
x1 is
x1
equal
equals
to
minus 2x.
2x2, right? This is what it says. This is what we obtain after reducing it to row echelon. X1 plus 2x2 is equal to 0.
Yes, yes.
And then what is x1? X1 is equal to 2x2 minus 2x2. Now you place this minus 2x2 inside
The
this
equation and
vector,
5. Okay.
right? So
Right.
you get minus 2x2 comma x2. Okay. It is a vector in R2. But since there is only one vector that is varying, it is on both of the coordinates. Now look at the coordinates, both of the coordinates. Okay, so at this point itself, you take. Uh, now let take x2 is equal to t. Okay, some variable t in R. So what will it become? It will become uh, minus 2t comma t, okay, where t is in R. Now you can take t out, okay, it is just common and it is nothing but the multiple, scalar multiple of vector minus 2 comma 1. So 2 comma 1 becomes the basis of the solution set. Now this solution set is nothing is what? It is this null space of A by definition, because we are looking at the solution set of this Ax equal to 0, which is nothing but the null space of A. So the null space of A is spanned by this vector. Okay. So what is the dimension of the null space? So
1.
this is the basis. Okay. Because there is only one vector, it is spanned by one vector. So that vector is linearly independent to itself, right?
Sir,
Basically, it is not linearly independent to itself. It is, but there is only one vector to, so there is nothing to compare. Okay, so it is one. So so that vector is span itself, and it is uh, linearly independent because there is only one vector. So that forms the basis. So the dimension is nothing but one. Dimension of the null space of A is one. Okay.
so
So
could you
the
please
vector corresponds
explain?
to dimension and null space is the same, you mean to say?
Sorry, can you say that again?
The vector corresponds to null space and basis is the same in this case.
This is the basis of the null space. Don't get confused that it is the basis of the row space. It is
Okay,
not the basis of the row space. It is the basis of the null space.
okay.
Okay.
Sir, could
So
you
don't
please
get confused with that.
understand why we have taken this minus 2t and t?
So uh, it is just a change of variable. So is it fine with you till this point?
Yes, 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 sir.
Right? Now
Right.
you just take, because x2 is varying in R. Okay. X2 is any real variable. So you can take x2 to be some t. Okay.
Okay.
Right? You take x2 to be some t. So
Okay.
that t I am writing over here. So minus 2t comma t. So this is what it becomes,
Okay. Okay.
right? And now what is this? This is nothing but the span of this vector minus 2 comma.
Okay.
Sir, can we say the dimension of null space to be the number of independent variables which we obtained during?
Right.
Yeah.
Yes.
Okay.
That is the dimension.
Okay.
That is the dimension of the null space. So in particular, it is the number of the. So now let me. So this is what we observed in this case. That what the number of independent variables, how many number of independent variables are there? There is only one independent variable. And how many dependent variables are there? One. So number of independent variable in the row reduced form is called the dimension of the null space. So let me write it down. So number of independent variable is called the dimension of the null space of a matrix A. All right. And now let me define a term which is called nullity. So nullity is defined to be the dimension of the null space of a matrix A. All right. So right. So nullity is equal to number of independent variables of row reduced echelon form, independent variables of row reduced echelon form of A. All right. And yeah, so we have seen two examples. So first example that we saw was of matrix. Let me write down that matrix as well. We saw this, uh, yeah, 3, 4, 5, 5. So this was our first example, 3, 4, 5, 5, whose row reduced echelon form was 1, 0, 0, 1, 0, 0, 1. All right. And second example, our matrix was 1, 2, 3, 6. And the row reduced echelon form of this is 1, 0, sorry, 1, 2, 0, 0. All right. So now let me make some space. Right. Now, by a definition, uh, now how many number of dependent variables and independent variables? First of all, how many number of independent variables were there in this first matrix?
Two in the
In this first
independent
this,
matrix.
there is no independent variable, right? Because there are two pivots, and both
Both are
of them are
dependent. Independent
both
variables.
are dependent, right? So there is no independent variable. So number of independent variable are 0. Number of dependent variable were 2. And we have seen that number of dependent variable is same as number of pivots, which is same as the row rank or column rank. And we have also seen that row rank and column rank are same. So which is nothing but the rank of the matrix A. All right. And number of independent variables, which is 0, which is by definition is the nullity of A. Okay. So what was the nullity of example 1? 0. What was the rank of example 1? 2. Similarly, what was the uh, now what is the rank? What are the number of independent variables in example 2?
One.
It is 1, right? Independent variable, number of dependent variable. So number of independent variable were 1.
One.
Number of dependent variables
One.
were also 1, right? Right. So nullity is nullity of A is 1, and rank of A is also 1. Clear?
Yes,
So we
sir.
have seen sorry. All right. Now let me give third example. Uh, Consider your matrix to be 0, 0, 0, 0. Now my first question is, what is the null space of A? Then
Exit.
nullity, and then rank of A.
Sir, all of them are zero.
All of them are 0.
No, sir.
Null space.
No, sir.
Uh,
Null space is 2.
no, I'm not asking the dimension. What is a null space? Null space is a span of vectors. So what are those vectors? What Not
Zero.
exactly the vectors, but what is the null space?
0, 0.
It will be all real numbers.
It will be, yeah, it will be basically, if you write down the definition, it is set of all vectors x in R2 such that ax is equal to 0. And now for any x1, x2 in particular, for any x1, x2, this will be true. So it is whole space R2 in that sense, right? Because x1 could be anything, x2 could be anything. If you multiply any vector, any two vector with this matrix, you will always get 0. So every vector is in null space of it. Okay. So null space is the whole R2. Okay. Now what about nullity?
2.
Right. Nullity is 2. Now what about the rank?
0.
0.
Right. Why it is 0?
Because
Zero
they
rows.
are all zero numbers.
Yeah, they are already in row reduced extent form and there is no pivot element. Right. That's the answer. Okay. So good.
There
Um,
is no non-zero rows.
there is no non-zero row. True. Um, okay, let's do one more
So
example.
nullity, number of independent variables. Nullity.
Number of independent variables. Right. So, for example, in this case, uh, if I look at this A, so in this A, what is the solution? What is the null space? Null space by definition is x1 comma x2 in R2 that satisfy this equation, which is ax is equal to 0. But in this case, every vector does satisfy this equation. So this is going to be the null space. But now let's take x1 to be, now I want to find out the basis. Okay, basis of null space. So how do we find that? So now x1, take x1 to be t1 and x2 to be t2. Both are varying in R. Okay, so it is going to be t1 comma t2. T1 is in T1 and T2 both are in real numbers. Okay. So there is a method to define to find out the basis. If there are two variables, uh, then you first take, if there are two TIs, then you first take T equal to 1, then T2 equal to 0. And in the second case, you take T1 equal to 0 and T2 equal to 1. So if you take T1 equal to 1 and T2 equal to 0, what do you get? You will get
1, 0.
1 comma 0, and in the second case you will get 0 comma 1. So they will be the basis of the null space. So it is 1 comma 0 or 0 and 0 comma 1. This is the null space. All right.
So this is the
So we
basis
will,
of the null space, right?
yeah, they are the basis of the null space.
Yeah.
Sir, x1
I'm,
comma 0, 0 comma x2 or x1 comma x2. Whole na?
uh, can you say that again? Hello.
Yeah, he was
Can you
asking if
repeat?
both the vectors are in the null, form the basis of the null space. That's what he was asking.
Yeah, they are the look. This is what I did. Right. I'm looking at the null space. I take x1 equal to t1, x2 equal to t1, and then you obtain this expression, and now you can take, because there are two variables, two TIs, so you take first 1 comma 0 combination and then 0 comma 1 combination, and then you get these two bases, these two vectors, and they will form the basis of the null space, because I'm looking at the null space. Right. Now let's do one more example to get more clarity on this topic. Right. So example number 4, I guess. Yeah. So let's take a set of these vectors. V2 is given by 0, 1, 1. V3 is given by 1, 1, 1. V4 is given by 0, 4, 4. So we have 4 vectors from R4. Now we need to find out the basis. We need to find out the nullity of this nullity. Nullity formed by the nullity of the matrix obtained by taking each vector as a row. So what I'm saying? First we consider the matrix. How do we get the matrix? By taking each vector as a row. Okay.
So we can remove V4, right? It's a multiple of V2.
Yeah, V4 is a multiple of V2. Yeah.
So we can remove it, right?
No, we are not.
Not right now. We are looking at the spanning. We are looking at the matrix formed by these rows.
Okay.
I'm not looking at the rank at the moment. I'm looking at the. So think of this matrix as of now, which is formed by the row. So A is a matrix with VIs as rows Ri. All right. So now we want to find out the basis of the null space of this matrix. So how do we do that? We apply the Gaussian elimination. So
R3 minus R1.
R1.
R3 minus R1, and so we get 0, 0. R2 remain as it is. R3 changes to 0, 1, 1, and then 0, 4, 4. Right?
Sir,
And then
R3 minus R2 or
R3 minus R2, R3 minus
minus
R2.
R3 minus
R4
R2, R,
minus 1.
R3 minus
correct?
R2 and R4 minus 4 R2.
1, 0, 0. Sorry, 1, 0, 0, 0, 1, 1, 0, 0, 0, 0, 0, 0. Okay. So we have obtained the row reduced echelon form, correct? So
Yes.
this is the row reduced echelon form of A. Now, what are the number of independent variables?
1.
X
One.
and
Huh.
X, Y.
Independent variable is 1, right? Number of dependent variable,
2.
2, right? So, what is the nullity?
1.
Nullity is
Nullity is 1.
1, rank is
Rank is 2.
2, right? Now, let's find out the null space of basis for the null space. Okay. So, what is the null space? Null space is set of all x1, x2, x3 in R3 such that Ax is equal to 0. And now when I solve Ax equal to 0, I obtain this expression. So now you multiply this vector with x1, x2, x3. So what do we get? We get x1, x2, x3, R3. You multiply 1, 0, 0, 0, 1, 1, 0, 0, 0, 0, 0, 0 with x1, x3. So you get x1,
Sir, 1 is
right?
used in the row 2. It's 0, 1, 1.
Yeah, right. X1 is equal to 0. Sorry, you get x1 and then x2 plus x3 and then 0, right? This is what you get. This is equal to 0, 0, 0. Sorry for the congestion over there. Let me shift this right. Oops. Mostly no. And this is equal to right. Okay. So this is what we get. In particular, we get two equations, which is x1, x2, x3 in R3 with x1 equal to 0 and x2 plus x3 is equal to 0 as well. Right. Now you can write x1 equal to 0. So that's what you can do right away. And then x2 is equal to x3. So you get x2 is equal to minus of x3. So x2 equal to minus of x3. So you get minus x3 in R3. Right. So you get this expression. And x3 is the only variable that is varying now. Because now you have reduced this vector in terms of x3s only. Okay. So x3 is the only variable that is varying in R. Is that clear till this point?
Yes, sir.
I haven't done anything fancy over here. Right. Now you can again take let x3 to be t in R. Uh, so you get 0 minus t. And since there is only one independent variable. So you just take t equal to 1 in order to find out the basis. You get 0 minus 1, 1. Okay. So this will be your basis. So what you get 0 minus 1 is the basis of null space. Okay. Null space of A.
So why we took t barabar 1?
Yeah, we took t equal to 1. That's uh, that's how you will find out the basis. You can think of it as a method. If there are two independent variables, then we will have t1 and t2. Okay, and then we will do like in the previous case. We took first t1 equal to 1 and t2 equal to 0, and then t1 equal to 0, t2 equal to 1 to find out the basis. In this case, we only had one independent variable, so we took t equal to 1 and find out the basis. It is just a method to normalize that. There is another way to see that. If you guys are comfortable, I can show it to you, which is just you can take t common, okay, in this. So you will get this. If you take t common out, if you take t out because t is nothing but a scalar, you can take it out. So you get this, and this is nothing but this. So you get a vector over here. So this vector is the basis. So this is what I do if I take t equal to 1. So there is no problem with that. Okay. So let me
So sir, any vector can be written as scalar multiplication of t.
not any vector. Uh, Vector from the null space can be written as scalar multiple of A.
Okay.
Right? Okay. So we have seen what we have seen till now. We have seen uh, the null space of a matrix or a given system of homogeneous system of linear system of equation. All right. And then we have seen nullity of A. We have seen uh, how to find out the basis of a null space of A. All right. So these three things we have seen. And we have also noticed that number of dependent variable is equal to the rank of a matrix and number of independent variable is equal to the nullity of A, and given a system of linear equation, the variables. So in a matrix, if a variable is not dependent, then it is independent. Okay, they are complementary to each other. So if it is either going to be dependent or it's going to be independent. If it is not, if a variable is not dependent, then it is independent. So what we have seen. So if you have a matrix, let's say A, which is 3, 2, 1, 5, 4, 2. So this is a matrix of 2 cross 3 type. So how many variables are there in this matrix?
3.
3, sir.
Right. Why 3 variables?
Because it has 3 columns.
It has 3 columns. Right. So whenever I say number of variable, that means you need to think of a matrix corresponding to some linear system of equation. And how do we obtain that linear system of equation? You just need to multiply it by x. So in order to we multiply from the right hand side. Okay. So while multiplying from right hand side, we need to make sure that this number 2 cross 3 and then this number should match. Okay. So that means the number of column, which is 3, must be equal to the number of variables. That's what she mentioned. So, and we have noticed that if a variable is not independent, if a variable is not dependent, then it is independent variable. Okay. So what we can write it now is that the number of dependent variable is plus number of independent variable is equal to the total number of variables. Okay. So in particular, rank of a matrix A plus nullity of a matrix A is equal to
Variables
the
of
number
n.
of columns, variables of n, and which is equal to n in our case. Total number, because you are looking at a matrix of m cross n type, so it is equal to n. All right, total number of variables. So for example, now let's do one more example where the so let's take this example. Example number 5, I guess. Consider this matrix. Consider this linear system of equation. X1 plus x2 is equal to 0. X3 plus x4 is equal to 0. X1, 3x1 plus 3x1 plus 4, 3x1 plus 3x2 plus 4x3, 4x4 is equal to 0. And x1 plus x2 plus x3 plus x4 is equal to 0. Okay. So let's find out the rank and nullity and the basis of null space of this linear system of equation. Okay. So first we need to find out the corresponding matrix. And how do we do that? What is the corresponding matrix to this?
All right, 3x1, 3x2.
It would be 1 1 0 0 0 0 1 1 and 334.
1100 334 1111. Right. I'm not writing the solution set because it is redundant. And now let's perform the row reduce extend form.
R3 minus
R3 minus
3R1.
3R1. R4 minus 4R1.
R3 minus 3R1.
3R1.
And R4 minus R1.
R4 minus R. Okay. So 1 1 0 0 0 0 1 1 0 0 4 4 0 0 1 1. All right. Now let's do what should we do?
Yeah.
R3 by 4.
Sir, R3 minus 4R2
And R4 minus R2.
and R4 minus R2.
Right. Zero vector here, zero over there. All right. So this is the row reduced echelon form. Now what are the dependent variables?
So two dependent, two independent.
Two independent, two dependent. Is everyone agree with that?
Yes.
Yes, sir.
Yes, sir.
Good. Now what are the uh, two independent, two dependent? So nullity is 2, rank is 2. That is clear. So let me write down. Nullity is 2, rank is 2. Okay. Now let's find out the null space. For null space, we need to just write down the uh, operation that we get. So if I multiply it with x1, x2, x3, x4, what do I get? So let's do that. If you multiply
X1 plus X2 equals to 0.
right, if you
And
multiply
X3 plus
this
X4 equals to 0.
right, so we get x1 plus x2, x3 plus x4, and 0 0. That is equal to 0 0 0 0. All right. So in particular, x1 plus x2 is equal to 0, x3 plus x4 is equal to 0, and we write the null space of A as x1, x2, x3, x4 such that x1 plus x2 is 0, x3 plus x4 is 0. In particular, we get minus x2 minus x4, x4, x2, and x4 are in R. Okay. Since there are two independent variables, let x2 to be t1 and x4 to be t2. Okay. And in order to find out the basis, what we do, we first take t1 equal to 1, t2 equal to 0, and then t1 equal to 0 and t2 equal to 1. So if I do in the first case, what do I get?
1 1 0 0.
So
Minus 1 1 0 0.
so let me first write it in terms of t1 and t2. Okay. Right. So what do I get? I get 1 minus 1 1 0 0 In the second, I get
0,
0
0, 0, minus
minus
1.
1. Right? So these are the basis of A, basis of the null space of. All right. Yeah. And in this case, again, we have seen that nullity plus rank is equal to number of total variables, which is 4. So 2 plus 2 is equal to 4. So this is called the rank nullity theorem. So we have seen this is the rank, not this in particular. Let me put it here. This is the rank nullity theorem. All right. So this is an example of the rank nullity theorem. And in this example, we have seen how to calculate the null space basis for the null space as well. Okay. Right. Okay. So now let me discuss one more topic of today.
In this case, can we take minus 1, 1, 1 minus 1 as T1?
Minus 1, 1.
Minus 1, T1 minus 1. Sorry, yeah, minus
T1
1.
equal to minus 1. That's what you're saying.
T2 also like 1 minus 1 like that. Minus 1, 1, 1 minus 1. Is it possible?
Then it is the linear combination of the first null space and second null space.
Okay.
Yeah, you will just add these. That's what you're doing. You are adding these two things.
Okay.
So this is
They
basis
will also be
minus
basis because you can take T1 and T2 could be any value in R.
That will be
Okay.
another
So it
basis.
doesn't matter what value you take.
That
But
will,
for simplicity,
yeah, that will be another basis, right?
that will be another basis. Whatever value you take of T1, T2, that will give you another basis. But for simplicity, we are taking 1 and 0 and 0 and 1
So
to get some simpler basis.
why I'm asking is here T1 and T2 are negative values. So it's okay to take 0 even if the variable's value is negative, right? The previous example you have taken minus 1 and 1 only. So that's why I
For example, if you take T1, T2 both equal to 0, then in that case, you will get 0 vector only. So that won't give you the basis. Right.
okay, okay, fine.
So in order to get the basis, you need to
Yeah, if more variables are there, we can do like this, right?
if for example, if there are let's say three independent variables, and in that case you have T1, T2, T3. So then you will take one T1 equal to 1, 0 and 0, then T1 equal to 0, T2 equal to 1, and then T3 equal to 0, and then T1, T2, 0, 0, and T3 equal to 1, like that. So that combination will go on. And for details, you can look at the slides of the uh, uh, notes.
We
So
have to avoid being 0. Like that way, we can take any set of values, right?
yeah, it's better to take 1, 0, 0 because that we always get basis. Other time you may need to check whether we are getting basis or not.
Okay.
Because in case of let's say if you take all to be 0, then it is not a basis. If you take some other combination also, uh, it might not happen. Yeah, I need to check that, but yeah, it won't happen. That is true.
Okay. And
Unless you take multiple of 1, that would be issue. For a multiple of everything is multiple of 1. You That's why you're taking 0. Uh,
okay, then it
is
will be
that clear to you?
100.
Ah. because it may happen that you might end up getting one basis or multiple of the first basis. That might also happen. So it is better to take 1 0 in this case. 1 0 0 and then like that accordingly number of variables, however variables you have.
Okay, thank you.
Yeah. Okay. So now how to check given n number of check n vectors of Rn form a basis or not. Okay. So for example, consider let's say 1 0 and 1 1. So how to check whether this forms a basis or not? Anyone wants to?
They're linearly
Uh,
independent.
they are linear dependent, but that is not enough to.
You can take the determinant, and if it's not equal to 0, they form a basis.
Yes. So determinant. Basically, we need to look for the determinant. So determinant is the answer. Okay. So in this case, clearly you can see write it as row wise. You look at the determinant of this, you will get 1 minus 0, which is 1, not equal to 0. So they form a basis. All right. Similarly, 3 comma 4 and 5 comma 6. Does this form a basis?
Yes.
How to check that?
No, it does not.
It doesn't. How to check that?
Check the determinant. So it's
Okay.
18 minus 20. So it's minus 2.
So
Yes, it forms a basis
Yeah.
because it is independent.
it is non-zero. It is non-zero. So whenever the determinant is non-zero, it it will form a basis. Okay. You just need to make sure that number of vectors. Yeah, give a number of vectors. So if you look at you form the row matrix from that, and then you take the determinant of that. Uh, and if it is non-zero, that means the given set of vectors forms a basis of R2 or Rn. So in this case, it does form a basis. Now, what about this?
Won't, because the second and
Not,
third are linear combinations of first.
no, sir.
It
Determinant is
doesn't.
0.
So their determinant should be zero, right?
Also,
So
like
let's check.
V2 and V3 are multiples of V1.
Ah,
So
right. So in this case, it is easier to see, but there can be tedious example where it is some weird combination of two vectors. Then it might be little bit difficult. So then you need to go for determinant checking. So in this case, it is 36 minus 36, which is 0, 2, 18 minus 18, and then 3, 12 minus 12, which is clearly 0. So it doesn't form a basis. Uh, what about this?
Sir, this is not a basis.
Not a basis? Let's find out the determinant. 5 times
Sir, the vector
9,
third is a
35.
linear combination of second and first.
No, it is not.
It is not.
2 vector 2 minus 1 vector 1. We are getting the answer with that.
You can just check the determinant. You don't need to look for linear independence because checking linear independency, it is tricky sometimes. Okay. So that's why you can go for determinant of the from the matrix with each row coming from from the vector, and then you find out the determinant of that. Okay, so in this case it is 36 minus 42 plus 3 times uh, 32 minus 35. You get minus 3 minus 6 plus 12, 3.
Minus 9.
All right, is 0. Yeah, so it doesn't form the basis. Correct. Okay, so this is what I was supposed to cover today. Uh, so now we can come back to the questions that you guys had uh, in the beginning.
Sir, I have a question with the cardinality of a matrix.
Right. Cardinality of a matrix.
Sir,
What does
like a
it even
matrix
mean?
vector is, and we have to find the cardinality of that vector.
Cardinality of the vector. Can you tell me the complete question?
So, please, sir, wait a minute.
There were some other questions as well in the beginning. Um,
No, sir.
Acha, you only had one doubt. Okay. Are you looking for the question?
Yes, sir.
Sir,
Yeah.
yeah, I mean, I had to confirm once again that in where we were converting to RREF, we were not very much concerned about that one more property, that it should be the only this pivot should be the only non-zero element in that column. So even if it would be in REF rather than RREF, it will have the same effects on null space or basis and other stuffs, right?
Yeah, that won't change.
Okay.
Rank and everything, these are independent of, uh, because you are calculating the rank remains same under these operations, row operations. So it doesn't matter.
Okay.
Cardinality of a basis, that makes sense. Cardinality of a basis is number of vectors in the basis. That is what cardinality.
So I have sent you the question.
Yeah, I'm seeing that. So your doubt is what is the cardinality of a basis of B? So what cardinality is nothing but the number of vectors in the base in the set of bases. So you need to find out in particular it's nothing but the dimension of B.
So how do we solve the question?
How to solve this question? Is it from this week's graded assignment? Then I am not supposed to tell you.
So I'm not
Um,
asking the solution. I'm just asking how to find it. Can
Let
you
me
give the
check.
idea of the cardinality of the basis of a method?
Yes, today's session is over. So if you guys want to leave, you can leave.
So I have questions on. I have a doubt in the activity questions.
In activity question.
Yes.
Okay.
So can I share my screen?
You can ask these questions in TA sessions as well, right?
Okay, so it's there on Monday, is it?
I think it's in this week as well.
Okay, so
Mm,
okay, then I'll ask it that time. Okay, thank you.
yeah, no problem.
Okay, so then can you tell the graded assignment 3 question that I had asked in the last session? The RR.
Yeah, right. So that question, uh, yeah. So you need to first form the. Uh, so in that question, let me see. Is that is this your question that healthy juice consists of 30 units of protein, 11 units of carbohydrate? Is that your question?
No, sir. It is the combination
Okay.
of capital capital R, small r, and small r. These genetics type.
Okay. Okay. Okay, I need to go through this question. So, uh, if you want, I can discuss this on Thursday as well. This question. Uh,
Okay, sir.
I was thinking there is some other question you had doubted. Is there any other question that you want me to have a
So
look and
how
let?
can we
Yeah.
find the intersection of a matrix
Intersection of a
of a
matrix.
matrix. Yeah.
Intersection with what? For intersection, you need two
Two
objects.
matrix, sir. There are two matrix.
Intersection of
We need to
There
find
are
the
two matrices.
intersection of that. Yes, sir.
It doesn't make sense. Either it needs to be for intersection, you need two sets. You can't take intersection of two matrices. So what is the set?
Okay, can we take the rank or dimension intersection? Intersection of two matrix dimension.
No, there is something missing. Uh, there has to be some vector space or some set whose intersection you are taking. And if you're taking intersection of two subspaces, for example, there are two subspaces which are formed by the span of those two matrices, right? So given a matrix, you can form a span of that matrix that gives you a subspace. Similarly, another matrix, there is a span of that matrix, another subspace. Then you can find out the intersection of these two subspaces, and then
How
your
can we
question
find
makes
that?
sense.
Can you explain?
Then your question would be like, uh, uh, so for
Okay,
example,
sir.
what I'm saying
When the
is
graded
there is a
assignment is done, I
matrix.
will ask it.
For example, there is this matrix A, and then there is this matrix B. Okay, and then you look at the span of these two matrix. So, for example, some SA. Okay, in particular, let's say V1 is the space spanned by A, and B2 is the space spanned by B. So, in particular, it is nothing but S and T times this. Okay, so this space uh, will look like such that A is equal to, so it needs to be in both of them. So this matrix A, B, C, D, it needs to be in both of B1 and in B2. So what does this mean? That we just now compare A, B, C, D with S, 2S, 3S, 4S. So this is one set of equation. Another set of equation we will get by equating these two, T00. And then now A needs to satisfy these two equations, that A is equal to S is equal to T, A is equal to 2S, and A has, and B, sorry, B is equal to 2S and B has to be 0. C is equal to 3S, but it also has to be 0. So this all will imply that S has to be 0. And if S is 0, right? But if S is 0, then T is also 0. So that means uh, zeros, that means uh, the intersection, they don't have any intersection. It is empty because uh, no, they have intersection, and the intersection is precisely uh, 0, 0 matrix. That is what they are intersection. Okay, so do you understand what I did here?
Yes, sir.
So that's how you can. So this is an example. Uh, yeah, I don't know what exact question you had, but this is what I think of the intersection of subspaces. For intersection, you need subspace. And how do you get the subspace from matrix? That's how one can get subspace. All right.
Yes, sir.
I think else we can have a look next time.
Thank you.
Thank you. Thank you guys for joining.
Thank you,
See you
sir.
on Thursday. Yeah, see you on Thursday.